And welcome back. As we continue talking about the interstellar medium, we need to kind of wrap up the third type of material, which we haven't yet discussed, which is that of cosmic rays. Now, in addition to the cosmic gas and dust that we have talked about previously, we do have a third class of particles, which is very noteworthy for the high speeds in which they travel and is often found in interstellar space. Cosmic rays were first discovered in 1911 by Austrian physicist Victor Hess, who flew simple instruments aboard balloons and showed that high-speed particles arrive at Earth from space. Now, the term cosmic ray is misleading, implying it might be something like a ray of light, but it is not light. Instead, they are actually particles, and they have nearly the same composition as ordinary interstellar gas. So, composition-wise, it's very similar to the gas that we've already seen. But as we will learn, their behavior is radically different from that same gas that we have discussed up to this point. So let's start off by talking about the nature of cosmic rays themselves. Cosmic rays are mostly high-speed atomic nuclei and electrons. Their speeds are actually equal to about 90% of the speed of light, so they are way faster than anything we have observed or talked about at this point. In fact, almost 90% of the cosmic rays are simply hydrogen nuclei, or the protons, stripped of their accompanying electron. You might also occasionally see things such as helium and heavier nuclei in about the other remaining 9%. And about 1% of cosmic rays have masses equal to the mass of an electron. And about 10 to 20% of these carry a positive charge rather than the typical negative charge that characterizes electrons. If you recall, a positively charged particle with the mass of an electron is referred to as a positron and is actually a form of antimatter. So again, these are all the things that we look at when we start saying what is actually in a cosmic ray. Now, the abundances of various atomic nuclei in cosmic rays very much mirror the abundances in stars and interstellar gas, but with one important exception. And again, we say it mirrors it because, again, what's the most abundant thing that we see? Hydrogen. What is the most abundant thing here in cosmic rays? Hydrogen nuclei. So if we look at, for example, the light elements, lithium, beryllium, and boron, these are actually far more abundant in cosmic rays than what we find in things such as the sun or in other stars. These light elements are actually formed when we have high-speed cosmic ray nuclei colliding with carbon, nitrogen, and oxygen, colliding with the protons in deep in outer space, and they actually are breaking apart. Now, cosmic rays reach Earth in actually a pretty substantial number, and we can determine their properties either by capturing them directly or by observing the reactions that occur when they collide with atoms within our own atmosphere. Now, the total energy deposited by cosmic rays in Earth's atmosphere is actually only about 1/1000th the amount of energy received from that of our sun. So it's a very infinitesimal amount, but it is comparable to the energy received in the form of starlight, which again is energy from other stars. Now, some of the cosmic rays come to the Earth from the surface of the sun itself, but actually most of the cosmic rays we receive are actually coming from outside of our very own solar system. And again, remember, these are traveling at about 90% the speed of light, so they are moving pretty quickly. So you might ask, well, where do cosmic rays actually originate from? Where are they coming from that they're so abundant? Well, this is a very serious problem to tackle when we're trying to identify the source of cosmic rays. Since light travels in a straight line, we can simply tell where it comes from simply by looking. Like, for example, stars, we know if we look at a star, okay, it's in that direction. But cosmic rays are not light. They are charged particles. And therefore, their direction of motion can be changed by things such as magnetic fields. And the paths of cosmic rays are curved by both the magnetic fields in interstellar space and by Earth's own magnetic field. So our calculations actually show that the low-energy cosmic rays may spiral many times around the Earth before actually entering the atmosphere, where we can actually detect them. So it poses a big problem in trying to figure out, okay, well, this cosmic ray came from deep in space, this one came from the sun. So what is our solution? There are a few clues about where cosmic rays might be generated. We know that, for example, magnetic fields in interstellar space are strong enough to keep all but the most energetic cosmic rays from escaping within our own galaxy. It therefore seems likely that they are produced somewhere inside of the galaxy. Now, the only likely exceptions are cosmic rays, which would have the very highest energy. Notice they have so much energy they can actually overpower the magnetic fields of our galaxy. And remember, the galaxy is pretty large. Now, we can estimate how far typical cosmic rays travel before striking Earth. If we look at the light elements lithium, beryllium, and boron, these are going to have the key for our answers. Now, since these elements are formed when carbon, nitrogen, and oxygen again strike interstellar protons, we can calculate how long cosmic rays have to travel through space to experience enough collisions to count for those light elements they contain. At speeds near the speed of light, again that 90% that we were talking about, it takes perhaps about 3 to 10 million years for the average cosmic ray to travel this distance. Now keep in mind that 3 to 10 million years is only a small fraction of the age of the universe. So cosmic rays must have been created recently on a cosmic timescale. In fact, even if we look at the age of our own Milky Way, the Milky Way itself is still billions of years old. So again, the cosmic rays are relatively newer, more recent phenomena. So where can we come from? Well, the best candidates for the source of cosmic rays we are finding is actually that of supernova explosions. And remember, supernova explosions mark the violent deaths of some stars. And we will explore this more later on about what type of stars this needs to be. Now, the material ejected by the explosion actually produces a shockwave. And we've talked about this a little before, about how this shockwave actually travels through the interstellar medium. It can actually heat up things such as interstellar gas. Keep in mind that when it does this, charged particles actually become trapped, and they bounce back and forth across the front of the shockwave many, many times. With each pass through that shockwave, the magnetic fields inside it accelerate those particles. Eventually, those particles are traveling so close to the speed of light, they can actually escape from the shockwave to become cosmic rays.